So this is our very last chain rule video, and the focus now is finishing the trig. So we did type 1 trig chain rule, which was when you had an angle that was something other than just x. And then we did type 2, which was something that had a trig function that was to a power. Well, type 3 is the combination of the two. So type 3, you're going to notice, is going to be the ones that have the most parts to the answer, is going to have a trig function to a power and an angle that is not just x. You will have four parts to your answer. I'm going to make a little list. I'll make it kind of in the middle. So your first part to your answer is going to be your power out front. Second part to the answer, you're going to take your original trig to a power 1 less. Then you're going to take the derivative of your trig function. So if it started out as a sine, take the derivative of it. And then finally, that last layer is you need to derive the angle. I like to think of it as like you're pulling back the layers and making sure you derive everything you've got. So I'm going to do 4 examples with you so you get to see kind of a variety and what ends up usually happening with these. So my first one, I'm going to do it down here so I have more room. So power out front is 3. Power 1 less, we'll drop it to sine squared. Derivative of sine is cosine. Now keep the angle the same. When you put the original power 1 less, make a little note here, your angle does not change. So if it starts out as 5x, it's going to stay 5x. Then finally, you're going to derive the angle, and then the derivative of 5x is 5. The only thing that can usually be simplified in this is going to be your coefficients. So you can write it as a 15 sine squared 5x cosine 5x. For your second one, so power out front, power 1 less, so it's going to drop down to tangent to the 5th. The angle does not change, it's still 4x squared. Derivative of tangent is secant squared. Again, angle doesn't change, it's still 4x squared. And then the derivative of the angle, and the derivative of 4x squared is 8x. So you're going to multiply the coefficients together to get 48x. And then everything else is just going to stay put. So you got a tangent of the 5th to 4x squared, and you've got a secant squared of 4x squared. So kind of pretty straightforward examples of this. Last two, leave them up a second. Again, when you're watching the videos, if you need to pause to kind of get ready to listen, that makes the most sense to me. So this next one I actually found on an old AP test, and I thought it was a nice one because it had some little things that were easy things to mess up, and I want to make sure you're comfortable with it. So we're starting out with power out front. Then we're going to take cosecant to a power 1 less. So you got to understand how to work with fractions. Power 1 less would be 1/3. Then you're going to take the derivative of cosecant, which is negative cosecant cotangent. This one gets kind of long. And my angles are still 7x cubed. And then finally, times the derivative of the angle, which is 21x squared. So when I saw this particular problem on an old AP test, this is not how they left their final answer. So we'll talk about that a little bit. What you can do is you can multiply the 4/3, the 7, and the 21 together or not your 7, sorry, ignore that. You can multiply your 4/3, your negative sign, and your 21 together to get your coefficient. So 4/3 times 21 would be 28, and it is negative, so you're going to get a negative 28x squared. So that's the first thing you can clean up. And then the next thing you can do is you have a cosecant to the 1/3, and then you have a cosecant to the first. Ignore the negative because we already pulled it out front. You can add exponents using your exponent rules and actually write it as cosecant to the 4/3 of 7x cubed cotangent of 7x cubed. So what you again are doing is you are combining like trig functions, adding their exponents to get the cosecant to the 4/3 power. And then finally, the last one, I purposely picked this one because I wanted to show you a shortcut. So if you look at something like this, I'm thinking your first thought should be, oh, there's a quotient rule here because we are dividing. Trig actually opens up a lot of options that can prevent you from having to do the quotient rule if you understand how to work with trig. Here's what I mean by that. Cotangent, you should know that cotangent is the reciprocal of tangent, meaning if I flip cotangent, the fraction, I get tangent and vice versa. So I could actually rewrite this as x squared tangent cubed 3x to the 5th. Another thing that I could do if I really don't want to do a quotient rule is I could use negative exponents. Personally, I don't love using negative exponents because my negatives always tend to get mixed up. So I actually prefer using this trig knowledge. I am going to have to do a product rule. I'm not going to be able to avoid that completely, but at least it takes a quotient rule off the table. So my product rule is first times the derivative of the second. So the derivative of tangent cubed is power out front, power 1 less, derivative of tangent, which is secant squared, and it's still of 3x to the 5th. Derivative of the angle, this gets very long, 15x to the 4th, plus second times the derivative of the first. So there's still even more to the product rule. So when I derive this, I just get 2x, and then the rest is just there, tangent cubed of 3x to the 5th. So cleaning it up just a little bit, I can multiply this x squared times this 15x to the 4th, and this 3. I guess I forgot about that. So 3 and the 15 would be 45. And then you have x squared, and x to the 4th is x to the 6th. And that's going to be with tangent squared 3x to the 5th, secant squared of 3x to the 5th. And then plus the rest of this, 2x tangent cubed of 3x to the 5th. And that is about as ugly as they can get because you are working with a more involved chain rule and you're doing a product rule at the same time. That is the end of the chain.